All right, so it's a pleasure to welcome our speaker today. It's Rosemary Guzman, and she is going to tell us something about extending the log to k-1 theory.
Hi, thanks. Yeah, eventually I'll get to that. So I want to sort of tell a little bit of a story. Right, so the big picture objective is that I'm going to tell you a little bit about how the geometry of a closed orientable hyperbolic 3 manifold interacts with its topological properties, okay, and in particular its fundamental group, and how together that gives me new information about M. All right, so that's my forest. And my trees, so in particular, I'm zooming in on this one fact, and I'm going to extend the log 2k-1 theorem of Anderson, Canary, Culler and Shalen to include words which, a set of isometries which is not necessarily freely generating. Okay? All right, so a fun quip which many of us have heard Dick Canary say, and I think it helps to provide some, get your hands on what hyperbolic space sort of looks like, right? So to play a comparable game of baseball, you'd need 10 to the 100 ball players to have the same amount of fun, right? Right, and you can see, I think Caroline Siri said this, right? I mean, you're looking at a hyperbolic surface there, and it has to curl up like a kale leaf in order to fit, quote unquote, in Euclidean space. All right, so there's our notion of parallelism, right, where in hyperbolic space, right, we're abandoning the parallel postulate, and at least all we're going to care about is with hyperbolic space, right, so given a line and a point net on that line, we have infinitely many points parallel to the given line. Models of hyperbolic end space, right, just to get everybody going. Right, so there's the Poincare ball model, and there I give it to you set-wise, the upper half space model. Now what's important are, well, what are the geodesics? I think once you know what the geodesics are, you really have an understanding of the space, right? And so in both models, they're just the intersection of the underlying set with a circle which is orthogonal to the 1-point compactification, right, of Rn minus 1. And there are just some examples of hyperbolic triangles, right, gotten by, right? So now we know what geodesics are, we can talk about triangles, right? So that's just the 2, 3, 7 triangle group there. I don't think I wrote that, but now you can see here on the bottom, right, these are examples of ideal triangles. All the vertices lie in S infinity, right? And notice, and I'll mention this later, that for any, so these triangles are all congruent here, and for any given one of them, right, so they each have, so pi over 2, pi over 3, and pi over 7 are the angles, right, and so you can see that the angle sum is strictly less than pi, and so just some interesting consequences of that very brief tour about the geometry of hyperbolic space, right, that the angles of a hyperbolic triangle determine its area, right? So it's just pi minus the sum of the angles. And given two triangles in H2, if their angles are congruent, then the triangles are identical, right? So, this is different from your notion of similarity in Euclidean world. In hyperbolic space, the shape of a configuration determines its size. So that's a very vague statement. I didn't write this, but you can think for n equals 2, you can think about Gauss-Bonnet theorem, right? And then Mostow rigidity for n strictly greater than 3. So I'll say something about that quickly. So what's a hyperbolic manifold? It's what you think it is. So it's a metric space where each point has an open neighborhood which is isometric to an open set in Hn. Right? These are the Riemannian manifolds of constant curvature minus 1. And the construction that we'll refer to today, right? So if you're looking at a subgroup of orientation preserving isometries of Hn, which is discrete torsion free, then the quotient inherits the structure of a complete hyperbolic manifold M. Right? And sometimes we'll say, okay, gamma acts co-compactly. Conversely, every complete hyperbolic manifold M is isometric to one constructed in this way. Okay? So from here on, right, you'll see me refer to this. So via our construction, gamma is isomorphic to the fundamental group of M, which is, of course, a basic topological invariant. Several of us are already familiar with the uniformization theorem, and I summarized it tried very hard to summarize what it would be for people who maybe aren't as immersed in hyperbolic geometry. So the idea is that, so these are ideas begun by Johansson, Jocko, Shalen, Thurston, and completed in 2004 by Perlman, and using ideas of Hamilton's, that every compact three-manifold has a canonical decomposition into submanifolds with individual geometric structures, each of which admits a locally homogeneous metric of finite volume, right? So problems of three manifolds were reduced to questions about hyperbolic manifolds. And 3 is special. The algorithm doesn't work for n greater than or equal to 4. I mean, you could just say there's a lot of, there's different ways you can explain why it doesn't work, and I'll just leave it as, well, oh, the Whitney trick doesn't work. I'll just leave it at that. Okay, properties of hyperbolic manifolds. Okay, mass-star rigidity. So given 2 closed orientable hyperbolic 3 manifolds, I could have also said finite volume or complete, whatever. If M is homotopically equivalent to N, then this equivalent is homotopic to an isometry. Right, so what does that mean? Well, then the topological classification of finite volume hyperbolic 3 manifolds is the same as classifying them up to isometry. Right? And of course, volume's a topological invariant. So again, I want you to, if you're taking something away, right? Shape determines size. Shape determines size. And I mean, for dimensions greater than or equal to 3, you get something that's stronger, let's say, than Gauss-Bonnet, right? I mean, so you can see this for n equals 2, but for n greater than or equal to 3, you get something a little stronger, although relating it to topological invariance is a little bit harder. It's more challenging. And Culler and Shalen have done some things like that, where they've made some statements relating volume and homology. And I'll summarize some of those. Okay, now, that volume is a powerful invariant in dimension greater than or equal to 3 follows from the fact that there are at most finitely many hyperbolic manifolds up to isometry of a given volume. Okay, so this finiteness property, I mean, makes this, so this is a really strong property. And just to, give you some notion of the rigidity of these things, right? So I just give one example here. So the Weeks manifold is a closed hyperbolic 3 manifold, and it's the one of smallest volume, right? 0.9427. So. Yeah, and so it was shown by Gabay and Meyerhoff and Miley that it was, in fact. So it was asserted to be the one of smallest volume, and I think probably about 10 years ago they showed that indeed it was. All right, so just some takeaways before moving forward. Hyperbolic manifolds are very rigid objects, right? Their shape is determined by their size. Closed orientable hyperbolic 3 manifolds are completely determined by their fundamental group, right? So that's really why I want to just examine that. And then there's a very intimate interplay between the geometry and topology. Okay, so here's the log 2k-1 theorem of Anderson, Canary, Culler, Shalen, and then Agel, Caligari, and Gabay are tacked on just because there was originally an assumption here of topological tameness, and Agel and Caligari, Gabay prove the Martin conjecture, which says that in this situation we don't have to worry. Every closed oriental hyper is topologically tame, right? So it's homeomorphic to the interior of a compact 3 manifold. We're good. Okay, so now here's the statement, and here's what I would like you to take away. So if I have K purely loxodromic orientation-preserving isometries of H3, and suppose that they freely generate a discrete subgroup, C, of rank K, then the idea is that at least one of these isometries must displace any point in hyperbolic space by a distance greater than or equal to log 2k-1. Right, so really take a second to absorb this, right? So this is, and this is common in hyperbolic geometry, right? Or in the study of hyperbolic manifolds. We're talking about something topological and geometric, and we're relating them in a very interesting way, right? And so this sort of interplay continues, right? And what I want you to think about is think about XC below as just a subgroup of gamma. So, in your head, later on, when I extend this, I'll be thinking about this. This in particular will be a subgroup
so
of.
You're saying that for every p, there exists some I such as Ci moves this point p by this log to k minus 1.
Yeah, as long as these are freely generating.
Yeah. Okay,
Yeah.
So, but that's what I meant in those modifiers. Okay.
Yeah. Okay, so I wanted to tell a story, which is why do I care to extend this log 2k minus 1 theorem? So let me step back a second again. So I should also say that earlier I said, well, to words which are not necessarily freely generating, right? So these are freely generating. And I'm going to care later on about a set of isometries which don't necessarily freely generate a subgroup of C of rank K, or the fundamental group. So keep that in the back of your mind. And the reason that I'm going to end up wanting to do that is, so one of my previous results, the phi free theorem. So if I have a closed orientable hyperbolic 3 manifold with phi free fundamental group, then there's a point in the manifold such that the set of all elements of pi 1 of m based at the point that are represented by loops of length less than log 9, they're all contained in a subgroup xc of rank less than of rank less than or equal to 2 in pi 1 of m.
Sorry, just read this again.
Sure. Right, so I'm thinking about so what I'm saying, so again, think about this, right? So that's right. Yes, that's the takeaway, right? All small loops, right, are, they live in some small group, right? And that will matter later when I'm trying to think about volume, okay? Now, a lot of people, so I was talking with Ilya about this. I was really excited that somebody knew what a k-free hyperbolic group was. It's just terminology that's not used very often. So I always feel, I'm like, well, let me sort of contextualize how special of a requirement. And it's really that it's not that special, like it's kind of natural, or it makes sense. So just to give you some feel for k-freeness, so we have a result here of Culler and Shalen. If k is equal to 2, then either the fundamental group of M is 2 free, or it admits a finite cover M tilde such that the rank of the fundamental group of M tilde is 2. And then for values of k, for when I'm looking for k free, k greater than or equal to 3, then we have a statement right with so I'm looking at the Z2 dimension of the first homology group here, right? And if that's larger than let's see. So you guys, I'm sorry, I should have said this. So I'm legally blind, so I can't really read my slides. So I have to go from, I have to remember this statement precisely. So I can't read them very well. But yes, so if the Z2 dimension is larger than 3k minus 4 or 6, right, then pi 1 of m is k-free, or, and this I think really makes sense, look at this either or and sort of ignore this, which seems a little obscure, but if you look at this as an either or, I think it really makes sense. Either pi 1 of m is k-free, or it contains a closed incompressible surface of genus less than or equal to k minus 1, right? So in other words, I think when you just look at those together, they make sense as an either one or the other, right? Okay, so Anderson, Canary, Culler, Shalen, and Culler, Shalen established results linking the geometry and topology of a closed orientable hyperbolic 3 manifold for values of k less than or equal to 4, and I'll summarize some of those. So a motivating question, going back to volume. Can the phi free theorem, remember in the end, we got this subgroup of pi 1 of m xc, which had rank less than or equal to 2. So keep that in the back of your mind. Can the phi free theorem and its generalization for all k, which I didn't list here, it's the implication theorem, I say it later, provide a possibly improved volume estimate from the current lower bound of 3.44? Right? And this is Culler Shalen. So we have to look a lot more closely at hyperbolic manifold groups. So here are some previous results summarized on one slide. So when pi1 of m is true free, what can I say about m? Well, I get log 3 as a Margulis number for m. And so if you're familiar with hyperbolic cylinders, what that means is that, and this actually comes from the log 2k minus 1 theorem, it's called the log 3 theorem. So if I take any two non-commuting isometries, if I take any two non-commuting isometries in isom plus h3, then they have to, given any point in hyperbolic space, at least one of them must always move the point by a distance greater than or equal to log 3. Okay, so that's one way to think about this. Okay, that's, I mean, there is a more general definition of Margulis number, but I'll sort of leave it there at that. The ball of injectivity radius, so we get the existence of this ball of injectivity radius log 3 over 2 in m. And what that means, if you're familiar with the thick-thin decomposition, right, is that I have a log 3 thick point. So I have a log 3 thick point in M, right? And so that's equivalent to saying there's a ball of injectivity radius of log 3 over 2 in M. And the volume is greater than 0.92, and that's using some sphere packing arguments of Meyerhoff and Brodsky. So for 3 free, this is Canary, Culler, Shalen, Agel, Culler, Shalen, we get a log 5 thick point. And what that sort of means is that so I'm actually curious, how many of you, are we familiar with the thick-thin decomposition here? Yes? Okay, so we have a log, okay, a lot of people said yes, that's good. So I have a log 5 thick point, or I don't know, at least I'm hearing the people who answered, or I saw nods. I get a ball of injectivity radius log 5 over 2, the volume was greater than 3.08, and what's interesting here now is that they have this statement relating volume and homology, and that was really revolutionary that time, right? So if the volume of M is less than or equal to this, then, you know, I make a statement about the Z2 dimension of the first homology. And then in the 4 free case, these techniques didn't generalize. There were a lot of subtleties, and it became far more complex. And while you may have heard of the thick-thin decomposition of M, right? So the thin part, those are like tubular neighborhoods, nice. Thick part is like a zoo. That's what David Dumas called it once to me. So it's like a zoo. I'm like, that's accurate. So we have a nice part, and then we have like a zoo part, right? Thin, thick. But in any case, now it starts to get a little nuts. So they were starting to say things like, okay, well, we can think about points which are lambda thin. Then we can think about, so lambda thin, lambda thick, right? You're lambda thick if you're not lambda thin. Oh, now we're going to also introduce a new kind of point, lambda doubly thin. And if you're not lambda doubly thin, then you were lambda semi-thick, okay? So, and it just started, I'm like, this is, so I was really motivated when I saw those things to feel the impulse to organize and clean up. There was something very messy about this, and I thought that there's something to generalize here maybe. And because these techniques differed so much from these others, I was just sort of curious to see what would happen. Now for the implication theorem sort of tells us what needs to be true. What needs to be true for me to make a generalized statement for k-free? Okay, so there's a group-theoretic statement that has to hold for the geometric statement to hold. Okay, and that's what the implication theorem. So once this holds, this is true. Now I show that this is true for rank 3 subgroups of a free group. Okay, so in other words, if the rank of, so if you have 2 subgroups of a free group whose such that the rank of their intersection is greater than or equal to 3, then the rank of their join is less than or equal to 3. Okay, and so Kent and Lauder and McReynolds had similar techniques for 2. That was very helpful. And results of the predecessors are just specific. If you sort of plug in 3 and 4, then that sort of explains everything that happened before. Okay, so I want to use this geometric data that I get from the phi free theorem, right? I have this rank less than or equal to 2 subgroup XC. And because I have in particular, if the subgroup has rank 1, that's easy. And Culler Shalen sort of took care of that. The problems are when, because we all know how free groups can behave, when this group has rank 2, right? Because if it has rank 2, well then, now subgroups can have arbitrarily large rank, right? Whereas when you're dealing with a cyclic group, well, every subgroup must be cyclic, right? Or, trivial. But the idea is that now, if the rank of this is exactly 2, there's a lot to think about. It changes things dramatically. And that's why I need an extension of the log 2k minus 1 theorem, right? Because I may not be looking at a set of k freely, so I'm not necessarily going to be looking at things which are freely generating. I'll be looking at subgroups here which may have rank, obviously possibly however large rank. And I'd like to say something about length 2 words contained in the rank 2 subgroup. Length 3 words, length 4 words. How do length 2 words move points in hyperbolic space? How do length 3 words move points in hyperbolic space? How do length 4 words move, etc., right? Because we know that, these are loxodromic isometries, right? And so after a certain point, after I'm, have so many of them together, after I, compose so many of them, then they actually take me far away from a ball that's mapped into the manifold, right? All right, so as I said before, results of Kenton, Lauder, McReynolds, they helped with the Group-Theoretic part in Culler, Shalen, and then I proved the analog for the 5 free case. And this is just sort of summarizing what I just said, right? So you can think here, if I'm looking at let's say gamma nu is my group XC, then I can have, arbitrarily large. This is just one example of a subgroup which is not rank 2, right? I can get them as big as I'd like. There are lots of different ingredients here that come into play for extending the log 2k minus 1 theorem, and I thought I should at least summarize some of them because I probably won't have time to get to a lot of them. So let's sort of look at an outline here. So we're going to talk a little bit about some combinatorics. There'll be some geometric group theory. We already discussed that. Some of it. We'll talk a little bit more. Some graph theory, and then a little bit of differential geometry because I'm going to need to use these Patterson-Sullivan area measures. Okay. All right. Okay. So so given a cover, what is the nerve, right? So if I have an index covering of a topological space by non-empty open sets, then I actually can extract from that an abstract simplicial complex, and we call that the nerve of the cover, okay? And it has the property that the vertices are in a bijective correspondence with the elements of the index set of the cover, okay? So in other words, to each set in the cover, I associate a vertex, right? And so let's say I have, so given, sets U and V in this cover, then if U and V have, so each of these gets a vertex, right? Sets in the cover, right? So it's in bijective correspondence with vertices in the abstract simplicial complex. Okay, so when do I join two vertices by an edge? Well, when I have non-empty intersection, okay? And you can see here, so here's would be the nerve of this cover, and then this one, so you see here they actually have, all three of them have non-empty intersection, and so I fill in the two simplex, right? So I actually have the two simplex, right, instead of just 3 edges. All right, so Borsuk's nerve theorem just says that the nerve is homotopy equivalent to the underlying space under nice conditions, and that's just, the conditions are that, the sets have nice intersections. It's just that the intersection should be open, contractible, right? And so that's the case, and what I'm going to look at, I'm going to think about these later as hyperbolic cylinders, and those certainly have, well, they have convex intersections, therefore certainly contractible, so I do get this property. So the takeaway from this slide is that due to this Borsuk's nerve theorem, with the appropriate cover, right, I can sort of discretize information and just look at the homotopy type of, of the abstract simplicial complex. Okay. All right. So what is a hyperbolic cylinder? So when I say maximal, I know I put it in, I did something special around it, which I can't make out right now, but I really want to point out that these are maximal cyclic subgroups, okay? Because I want, when I talk about two maximal cyclic subgroups, then naturally I don't have to worry about, you know, their elements commuting, right? Okay, so that's why I want them to be maximal. All right, so now I'm looking at the, so here's the definition of a hyperbolic cylinder, right? It's just the points in hyperbolic space which are displaced by whatever isometry I'm talking about, you know, by distance less than lambda. Okay, and for my purposes, given the log 2k minus 1 theorem, I'm going to let lambda naturally be log 2k minus 1 in everything I do, right? Because I'll get some nice results. Okay. All right, so this is, of course, a locally finite family, and all that means is that every point in hyperbolic space is only contained in a finite number of them, right? Anyway, so that's a locally finite family, and it has a natural association to the set of maximals.
Why do you call it a cylinder?
Okay, so it really looks like a banana, right? So think about, this is a loxodromic isometry that I'm thinking about, right? And so obviously it has an axis, right? A translation length, whatever. And so all of the points that are displaced by a distance, let's say less than lambda about that, you know, they're sort of like, I get this banana shape.
So somewhere close to the displacement.
Yeah, yeah, right, yeah. Okay? Yeah, thanks. Okay. All right, so, and now what I want to do, remember we were talking about, you know, we were looking at a generic open cover on the last slide, and I said I wanted to construct the nerve. So it's not generic anymore, so the open cover I'm going to want to look at is I'm going to want to look at the cover of hyperbolic space by cylinders. And it's going to be a certain, you know, it's going to be the union of, let's say, a threefold intersection of hyperbolic cylinders. And I don't go into all of that detail, but anyway, that'll be the idea. It won't just be covered by one hyperbolic cylinder or not. That would sort of be like Culler and Shalen, right? If you're in one hyperbolic cylinder, right, then if a point is contained in some hyperbolic cylinder, then it's in the thin part, right? And if it's not in any hyperbolic cylinders, it would be in the lambda thick part, for instance, right? Since we're good with lambda thin, lambda thick. Okay, and then you just have to think about this now up a few notches, right? Instead of just being covered by one cylinder, right? You know, they had this doubly thin and semi-thick thing, which wasn't working super well because, well, if you're doubly thin, if you're in two cylinders, well, if you're in two, okay, well, what does it mean to not be in two? You could be in one only or none. So, right, so it wasn't perfect. And this isn't either. That's why you have to keep working on this thing. All right, so the idea is that now, like I said, I'm going to replace the open sets in the cover in the last slide. I'm going to be replacing them with these maximal hyperbolic cylinders. And so again, this idea that I'm going to think about, now you're thinking about your abstract simplicial complex, and to each vertex in the abstract simplicial complex, I'm associating one of these, right? So when you think vertex, you immediately should be thinking of the associated maximal cyclic subgroup, right? So that's why I denoted C sub V, right? So each of these maximal cyclics is associated to some vertex in the abstract simplicial complex. All right, so that's a gamma-labeled complex. Uh-oh, that was timed out here. All right. Oh, good, okay. Anyway, so just an example, if I have a point which is in n+1 hyperbolic cylinders, right, then indeed I have this corresponding n simplex in the nerve. All right, a little bit of some group theoretic stuff here. So now that we're thinking about this abstract simplicial complex where I'm associating to each vertex a maximal cyclic subgroup, well, I want to now think about an associated subgroup to each simplex in the nerve. Okay, so that will be theta of sigma, right? So if sigma is a simplex in the nerve, then I want to look at all of the maximal cyclics, the group generated by all the maximal cyclics, such that those maximal cyclics have a corresponding vertex in sigma. Okay. All right, so as a silly, kind of a quick example. So if tau is just, this, so tau is just an edge, v naught v1. If that's just an edge in the abstract simplicial, in the nerve, then there's a point by default in hyperbolic 3 space which lies in the intersection of these cylinders, right? Remember, these correspond to sets in the cover, and a simplex is formed when there's not empty intersection. So there's at least, there's a point in the intersection of these. And now, so theta of tau would just be, right, the group that's generated by the associated maximal cyclics. Clear? Is that? All right, now, so I had to, in order to deal with this problem later on of this rank 2 subgroup that I get in the conclusion of the 5-3 theorem, I had to induce a lot of new definitions on this thing, one of which is very long, and I'm like, maybe I should have called it something else. The minimum enveloping rank. Okay, so if H is a subgroup of G, then the minimum enveloping rank is going to be the smallest rank among all the ranks of groups for which H is a subgroup if such a number exists. Right, so say for example, you can have, with free groups, you could have, let's say, like I showed you on the previous slide, we had like a rank 3 subgroup contained in a rank 2 subgroup. So the minimal enveloping rank would be 2, because although it itself was rank 3, right, and it's a subgroup of itself, well, it's contained in a rank 2 subgroup, and the smaller of 3 and 2 is 2. So that particular subgroup of rank 3 actually has minimal enveloping rank 2. Does that make sense?
Why wouldn't it exist?
Oh, such an, okay, well, what if it's not finitely generated? Yeah, okay. Okay, and now, so this is, I call the funky subcomplex, the minimum enveloping rank subcomplex, because it's so many words to trip on. So funky subcomplex will mean this. And what it is, and it is indeed a subcomplex. I know it's good if you're suspicious, but I promise it is. And it's the subcomplex of the nerve which consists of the non-trivial open simplices such that the minimal enveloping rank of theta of sigma is less than or equal to n. Okay, so so this is in fact a subcomplex, right? So remember, I could have, like in that silly example I had before, right? I had this rank 3 subgroup in a rank contained in a rank 2 in a rank 2, and so, well, in that case, while it had rank 3, for instance, well, if I let n, if I'm looking at k sub 2, then that thing would actually be in this subcomplex k2, because while itself it has rank 3, it's contained in a rank 2 subgroup. Okay? So this just kind of helps control some of what happens with free groups, right? Because we can get, so that's sort of what I'm trying to do here. Now it turns out that if every point in hyperbolic space is in, oh, are we getting low on? This is a sign to not put as much on a slide. I get it. It turns out that if every point, yeah, is in greater than or equal to k minus 2 cylinders, then the nerve minus the funky subcomplex is actually homotopy equivalent to H3, and therefore it's contractible. This is true if pi 1 of m is k-free. Okay. And the reason it's well, this again, Borsuk's nerve theorem happens here. There's some stuff. There's a lot of stuff, but it's, you're taking away a lot, and it's really amazing to still know that what you're left with is still contractible. So you do take out a mighty chunk. And I should add, with great respect for Culler Shalen, they looked at something similar, but they were just looking at they were looking at basically the skeleta, right? Which certainly doesn't work for the generalized case, right? So instead of taking away, this minimal enveloping rank subcomplex, maybe they removed a certain part of the 2 skeleton. They removed a part of the 2 skeleton, for instance. All right, so just some group theoretic stuff, and just to make sure you have an idea on, or see the purpose or for the need for this idea of minimal enveloping rank of a subgroup. Well, it's generally not true, right, that if tau is a face of sigma, it's generally not true that the rank of theta of tau would be less than or equal to the rank of theta of sigma, right? These are these problems with free groups. However, it is true that the minimal enveloping rank of theta of tau is less than that of theta of sigma. So I get this linearity property that I didn't have before, right? Because the thing is, when you're dealing with free groups and you add in some new element, right? I mean, you get fluctuations in the rank, right? But the minimal enveloping rank, right? When you add in new isometries to your big mess, it can either stay the same, or the minimal enveloping rank can go down, right? But I don't get this. Does that make sense of why, you get this linearity kind of thing? All right, so I sort of tried to summarize here, and I didn't state a result that kind of, I think, highlights this just for purposes of time. It's sort of an extension, a second version of the extension of the log 2k minus 1 theorem, but it's just similar to what this says up here. All right, so this is what I mentioned before. This group-theoretic statement was necessary to show the geometric statement in the phi free case. There's sort of a, not gonna, it's a long argument to talk about that thing in itself, so I'm just going to hand wave over that because that's like a whole nother talk. All right, so just some other things that I need. Well, going back to our nerve minus funky subcomplex, well, I actually get that, remember we found that it was contractible and it was, via some, some stuff that I hand wove over. But so I can write it as a disjoint union of saturated subsets realized for open simplices, such that, and that should be minimal enveloping rank there. The minimal enveloping rank of theta of sigma is k minus 2 or k minus 1. So that's it. Like so I started off with this, a cover of hyperbolic space, and now I've written it, as a disjoint union of these things. And later on, we're going to, well, we'll say more. Now I'm going to examine, so here, I want you to think of this abstract bipartite graph, right? So I'm thinking about components of this set here, and I'm thinking about components of that set there, okay? And I join vertices. So each vertex represents a component, okay? And I join by an edge if there's something in here which is a face of something in here, or vice versa. So if there's a simplex in here, which is a face of a simplex in there, right? Or the other way around. Okay? All right, so what does it mean? I think, this maybe goes without saying. All right, what does it mean for gamma to act on the graph without inversions, right? It's what you think it does, right? It stabilizes the vertices. Each vertex is fixed. So by way of contradiction, the thing is showing the existence of a tree, which actually happens to be a homotopy retract of this thing, right? Which we showed was equal to the disjoint union of those two subsets up there, and it's actually connected and simply connected, okay? And I'm able to show that there's an action by gamma without inversions having the property that the vertex stabilizers are free, and by Stallings, and well, I know I wrote Culler Shalen, but really it kind of comes from Stallings as well. That can't happen. Right? I mean, for a closed orientable spherical 3-manifold, pi 1 of m cannot admit a simplicial action without inversions on a tree with the property that the vertex stabilizers are locally free as a subgroup of the fundamental group. Right? This is a more specific statement that comes from Stallings. All right, so that establishes the phi free and implication theorems. Let's go back. What would I get? Why do I want to extend the log 2k minus 1 theorem? Remember, volume is a topological invariant. This is where I'm going. And I want to come back. And knowing what I know about the phi 3 theorem, knowing what I know about this just let's say, it could be rank less than or equal to 2, but we'll just say rank 2 for the purposes here. Subgroup XC of the fundamental group of pi1 of m based at p. I know some topological information, and I'm going to use that to tell me something about the geometry, right? All right, so how can I use this to tell me about the volume of M? So it shouldn't be a surprising me, right? So I know something about how I know something about how these, as Ilya said, right? These isometries that move this point by a short distance, they're kind of in a small subgroup, right? So what's the method for strengthening the volume bound? Okay, so by default, I can use, I'm looking at a 5 free group, which is naturally 4 free. So I, of course, can use the bound of, that's true. I get what comes out of Culler and Shalen, but I can improve this. I have more information, and I have a lot more to deal with this rank 2 subgroup, but what's the method going to be? So the nearby volume and distant volume. So I want to find bounds for the nearby volume, and so this is a similar idea that Culler and Shalen had, and also I want to find a bound for the distant volume, and then you can think, well, if I'm looking at a certain neighborhood of my point P for my theorem, I'm looking at a log 9 over 2 neighborhood, and then if I look at the complement of that, in theory, if I'm able to say something about each of those volumes, I add it together, that's a lower bound for the global volume of M. And I don't know how much time, so I wrote a summary page. I don't know how much time I have to talk about the paradoxical decomposition in Poincare series. So at least I have a few pages of summary, and then maybe I'll spare you past some of the sausage being made. Nobody wants to see the sausage being made. All right, so the paradoxical decomposition. All right, so it's a Banach-Tarski style decomposition of the Patterson-Sullivan area measure, which is just an n-1 conformal density with Poisson kernel, which given by a conformal expansion factor, and I'm going to apply that to length 2 words of my rank 2 subgroup XC of the fundamental group of M. So I'm actually, if you think about it, and this is very ad hoc, it's like, well, okay, so for elements in XC, I have an upper bound on displacement from the phi free theorem, right? Because those guys are moved by distance, right there. These correspond to loops of length less than log 9. And then, okay, well, from the extension of the log 2k minus 1 theorem, which I'll say finally at the end, then I'll have I'll sort of be able to say, all right, I'll have a lower bound. Like, there has to be some isometry which moves P by a certain distance. And I'm going to put these two ideas together for like a nearby and distant volume kind of thing, which I just spoke about. All right, so yeah, it's just a restriction on the ambient geometry, and I'll be looking at a ball minus caps model on a log 9 over 2 radius ball in H3. So this isn't perfect because my workstation fell apart 2 days ago, and no, it really fell apart. Had to be hauled out by the IT people, and I needed to write a tilde on here, but that's okay. So you'll just remember what I say. So remember, P is a point in M, but I'm actually, so P tilde is a point in the pre-image under the quotient map, right, that takes H3 to H3 mod gamma. So P tilde, these should be P tildes, is just some point in Q inverse of P. All right, so yeah, I'm talking about H3 right now. I'm not in M. That's what I'm just trying to say. So think of that, this is the pre-image of P that we were talking about before. This is really a rudimentary example. All right, so here's sort of what I'm talking about. Now remember, if I had my subgroup XC of the fundamental group of M, let's say it's generated by gamma and nu. Okay, and so those have to displace P by a distance less than log 9. So I'm looking at a log 9 over 2 radius ball in H3 because I'm later on thinking about the intersection of this with a Dirichlet domain, right? And so that's why I'm looking at a log 9 over 2 ball. Anyway, so when I say I'm going to look at a ball minus caps, all right, so if this is, so if P is moved, so P, let's say, is moved to here by gamma, and so you can say, or so gamma of P is here, is what I'm saying, right? Then you can think, well, this part, when I map into the manifold, right, the quotient matrix does not contribute to the volume of M, right?
Contribute more than what's inside.
Yeah, right? And of course you have to think about the inverse here. I mean, like I said, this is, but then the picture got too busy. So, right, there's, gamma inverse, and, but, there's a very complicated thing about when you have overlap of the caps. But anyway, this is just sort of a vague, easy example to understand, okay, what's going on. And when I take the quotient of this into the manifold, these don't contribute to the volume, right? Now, what's going on over here? This was, like I said, a rudimentary sort of example. The log 2k minus 1 theorem extension guarantees that I'm going to have a length 2 word. Doesn't have to be this one, but when I wrote more, there was too much on the slide. So there's a length 2 word, doesn't necessarily have to be gamma nu, but there's a length 2 word that displaces P by a distance greater than or equal to log 5. So what I want to look at is I'm looking at, okay, I'm looking at what's happening when I map this into M and what I can say about the volume here, a lower bound here, and then also around this point. All right, so that's my distant volume, and I'm going to leave, there's a lot of details, and it's not easy, and I'm working on this volume problem, and it's not a short problem, and it's something I'm still working on, but I have the extension done, which I guess I'll finally at some point. Let me see, all right, so I better skip to it. I've got 4 minutes left, so I'll spend 2 minutes on this slide and then tell you the extension. All right, question?
So what's the extension now?
Really? Okay, this is, all right, how about I just say this because I use this on the next slide. So, I'm going to decompose this rank 2 group in the following way, right? So I can certainly do this. So I'm going to look at words with length 2 initial syllable, and then, right, disjoint union, the length 1 words, and then, of course, the identity element. But I can certainly decompose XC this way, right? You either are the identity, a length 1 word, or you have your length 2 or more, right? Okay, so there's 12 length 2 words, right? Don't forget inverses. Okay, and so I will skip everything about dun, dun, dun. There we go. Okay, there's the extension. Okay, so if I'm given, purely lexicodromic gamma nu, freely generated discrete subgroup of rank 2, then the point is that given any point in H3, if I look at the how it's displaced by all of these length 2 words, at least one of them must displace P by distance greater than or equal to log 5. And the reason this is really needed is because, again, so this is for length 2 words. Right now I can say something about, here's how length 2 words move P within this log 9/2 radius ball. I can generalize this. You could use the same method. I have a statement for length 3 words. For length 4 words, and once the length of the word is long enough, you're not even contributing to the volume anyway, right? And you have to make some restrictions, but once you are able to say how length 2 words, right, and these 12 length 2 words certainly are not freely generating. They don't freely generate a rank 12 group, right? I mean, so this is the idea that it's different, and but it's on my way to saying something about, finally at last, about the volume, right?
So alpha beta actually has 3 reduced lengths too, right?
Yeah, it's one of the length 2 words, yeah. And then, using the same technique, although I haven't made it so neat yet, I have, some kind of a statement for length 3 words and stuff like that. And then it's just putting everything together. Yeah, so, all right, thank you. Okay, I do have something fun.
Actually, could you go back to the
Yeah, sure.
the theorem?
Right. Oh, okay.
All right. Are there any questions? Okay. Thank you very much again.
Thank you.